Hey guys, Unit 5, Astronomy. Your book is an awesome resource for this. Chapters 26 and 28. Astronomy is defined as the study of the universe, you guys. Earth is a planet and beyond. So people ask sometimes, Ms. Polson, this is Earth science. Why are we studying the universe? And that's because Earth is a third rock from the sun, and where's our place in the universe? We study Earth as a planet and beyond. Looking at the scale, starting big, we have the universe that has everything in it, and if you look at this image, this back dusty looking material is the whole universe. If you zoom in on a little spot on that, you're going to see the galaxy superclusters. Believe it or not, even though these galaxies are super far away from each other, they do influence each other with their gravitational influence. So they cluster together in superclusters. If you zoom in, if you can look at my cursor, if you zoom in on the supercluster there, you're going to see the local group. We have 30 galaxies in our local group. That's kind of like our neighborhood. 30 galaxies. If you zoom in on a section on the local group, you're going to see our Milky Way galaxy. It's a spiral galaxy. Look at it in its beauty. This is the artist rendition. And if you zoom in somewhere around on this arm right here, you're going to see our solar system. And if you zoom in on our solar system, you're going to find planet Earth. There we are. Hello. The fun facts, you guys, are not going to be tested on these, but we do have a couple of definitions in this section. So the definitions you need to know, and I'll tell you to star them. So how many solar systems are out in our galaxy? Many. So far there's been 70 discoveries, and we have new discoveries every year. We have actually, that number is more like around 100 plus, because we have a Kepler telescope out there that are discovering more, at least, every couple months I hear about new discoveries. How many stars are in our galaxy? I showed you guys that picture of all the stars in that, and it looked like sand. It's estimated between 200 and 400 billion. Basically what they do is they take a section of our galaxy, they look at it, with the help of computers they're able to count them, and then they extrapolate that out to the size of our galaxy, and they figure 200 to 400 billion. It's a lot. How many galaxies are in our local group? Remember our little neighborhood? There are 30, including Andromeda, which is ginormous. How many galaxies are in the universe? Hubble has observed over 3,000, but it's estimated that there are over 500 billion. That's crazy. Hubble hasn't looked at every space yet, so that's why the satellite's only seen 3,000. But from what it has seen in the area that it's looked at, if we extrapolate that out, it's over 500 billion. You guys, remember galaxies are billions of stars. So if there's over 500 billion galaxies, it's big out there. That's a little cut off, but it says scale, it's big out there. These are, this is something that you're going to need to star in your notes. 1 astronomical unit is 93 million miles, and that represents the distance from Earth to the Sun. 93 million miles. Miles is difficult to use in astronomy because it's such a small unit, because it's so big out there. So using miles as a distance unit is the equivalent of me asking you how many centimeters it is to Battle Creek. That's just silly, ridiculous. The number would be so ginormous it wouldn't even matter to you, make sense to you. So astronomers have established, okay, we need units of distance, and something that we can connect with and understand is the distance from Earth to Sun. So that represents 1 astronomical unit. And just to give you perspective, our solar system from the Sun to Pluto is 40 astronomical units. So if Earth to the Sun is 1 and the Sun to Pluto is 40, that gives you a little perspective on how big our solar system is. To the center of our galaxy, we have 26,000 light years. You need to star light years because you do need to know that definition, and that is the distance that light travels in 1 year. It's 5.9 trillion stinking miles. It's ridiculous. Huge. And please remember that it is a unit of distance, okay? Even though you can infer time on that. Another little interesting fact, we are a spiral galaxy, and I did show you a picture of what a galaxy looks like, and that galaxy is rotating, it's spinning, and where we are on the outskirts of our galaxy, we are traveling, our little solar system with our sun and all the planets are all traveling together. We're traveling at a speed of 220 kilometers per second, and it takes us 230 million years to make one revolution around the center of our galaxy. Crazy. Milky Way diameter from one end to one end is 100,000 light years. So if there was a star on the other end and you were standing on a planet on one end and there was a star on the other end, it would take you it would take light from that star 100,000 years to get to you. So you are seeing that star as it was 100,000 years ago. Think about that. Think about that. That's pretty crazy. The sun to the nearest star, Alpha Centauri, is I think it's a triple star system, and it is 4.3 light years away. That's our next nearest star. That's our neighbor. And it takes that neighbor 4.3 years for that light to come across space. That's how far away it is. So even though light years are a distance unit, you can definitely infer time with it, which is kind of fun and unique. Our next door neighbor, it's not really our next door neighbor, but the Andromeda Galaxy is part of our local group. And remember how I was telling you that was part of our neighborhood? So on the block, our block is still 2.9 million light years big because Andromeda is that far away from us. So it's still really, really large, our little local neighborhood. And Andromeda is, like I said, ginormous. And it is traveling toward us, but it's projected not to collide with us for a long, long time. It's got to traverse the 2.9 million light years to get to us. The limit of our observable universe, I think it might be cutting off right there, but it's about 15 billion light years. That's about how far we can see. It's about how far our technology will allow us to see. All right, you guys, at some point you're going to be looking at these fun links and answering some questions potentially. You're not going to see those right now, but I invite you to look at them at some point. Here's a picture of the Milky Way. It's an artist rendition. Obviously we can't get a picture of our own Milky Way because we're in it like this, but here we are off the side, and the motion is counterclockwise. It's moving this direction. And this is what Hubble sees. It's also a little bit of what we see. Hubble is a little bit more sharp in its perception because it doesn't have the atmosphere that we have that interferes with what we can see. So it looks like somebody took a spray can, sprayed it, but that is us looking at the center right here. If we're looking toward that direction, we see a concentration of stars, and this actually extends out from the sky like a beam, I don't know, like a line, and it's concentrated there. Those stars combine their light, and it makes it look like very blurred. You can't really see individual stars. Pretty cool. You guys are asked to draw the anatomy of a star. I'm calling it the sun, and anytime I refer to the sun, I'm really referring to any star. Any stable star has this structure. So on your notes, you have a bold black line. That is going to represent this dark yellow line right here. That would be your black line on your paper. And so we have the convection zone right here. Convection, the energy is coming out through waves, through the plasma, like bubbling up. And then we have our radiative zone right here. You need to label that, draw that in and label that. Put a little arrow, put a little line right here and extend it out and put radiative zone. That energy is being transferred from the core outward through radiation. High craziness is happening in this core right here. So label that core, and I would also put fusion right next to that word core, because that, my friends, is where the temperature is hot enough, pressure is hot enough. That is where fusion is. Only right here, not anywhere else, right there. That is the hottest, highest pressure area in which fusion can then take place. And then outside your black line right here, outside that, you should draw in another circle around that, and this part of this needs to be labeled chromosphere. Chromosphere is the innermost atmospheric layer. Yes, the sun has an atmosphere. So label that. And then the outer atmosphere is called the corona. And draw a little line there and label that. That's the outer atmospheric layer. Can't remember if I said the photosphere. So draw a line like that and label that photosphere if you didn't do that yet. So now you know the anatomy of a star. Be prepared to answer questions about that. And later when you learn a little bit of vocabulary, you're going to associate some of these areas with some of that vocabulary. So photosphere is the surface of the sun. Why don't you take a picture of it? That's what you would see if you looked at the sun. That's the surface. I would go ahead and put surface by your label. Moving on. Sun structure and makeup. Plasma. There's 3 states of matter. Plasma is the 4th state of matter. You have solid, liquid, gas, and plasma. Plasma is charged particles. You've got a cesspool of charge, just boiling up, moving around, electrons, protons, craziness. We do have plasma on the planet. We have plasma screen TVs. They work by charged particles. This is a plasma ball that you probably have seen before. I'm going to show you that in class. Basically, you have energy being exchanged off there, exciting the atoms that are inside this ball to the point where they become ionized and they emit light, and that, right, my friends, is plasma, and that's why it's called a plasma ball. So stars have elements in there that exist as plasma. Not as a liquid, not as a gas, but as plasma. The 2 most abundant elements in stars, and you definitely need to know this, are the 2 lightest stars on the periodic table, hydrogen and helium. Hydrogen's the lightest, helium's the next lightest. And they are the most abundant in the universe too, my friends. Okay, the surface of the sun has dark spots. Has dark spots on the surface called sunspots. And they are cooler temperature, but you can actually see the bubbles from the convection happening on the surface, and you can kind of see how it's granular looking. But the sunspots are associated with the north and south magnetic poles. So there's always usually a couple of them that occur together, and what you don't see, but what's there, are magnetic field lines that loop between the 2. And those will show up in another vocabulary word called a prominence. But sunspots are on the photosphere, the surface of the sun. Why don't you take a picture of it? It's photosphere. You're going to get sick of me saying that. And anyway, they are associated with magnetic fields. By watching the sunspots on the surface of the sun, we can tell the direction that the sun is rotating. Even though it's fluid, it does have a rotation rate. And it's 25 days at the equator, 34 days at the poles. And so, therefore, it's traveling faster. Where? Where is it traveling faster? It takes less days for it to move across the equator, so it's traveling faster at the equator. Like I said, they're associated with strong magnetic fields. The sunspot cycle, it peaks every 11 years. So there will be times when surface is no spots at all. And then there are times when it looks like this. This picture was taken in 2001, and I love it because it shows you the perspective of Earth. Look at that tiny little Earth. When I told you guys about the beach ball and the sand grain next to it, the beach ball sun and the sand grain Earth, give you a little perspective. Sunspot cycle peaks every 11 years, and that's what's shown in this graph. We have a peak, valley, and it pretties consistently every 11 years. Sunspots are also associated with another vocabulary word called solar flares. Watch this video. You can see that release. Once that release of energy comes across and hits the satellite, static. Satellites are electronic, and they don't do well with all that energy coming across, so we actually lose satellites as a result of it. The solar flares are sudden outbursts. Right here is a solar flare in this picture, and it's associated with sunspot activity. Increase in sunspots is an increase in solar flares. And I think my time is going to stop, so you're going to have to continue on another video.